Okay, so we talked about momentum and the conservation momentum. We talked about the change of momentum. I just want to kind of look at that in a different light. Remember, J is impulse, is the change of momentum. And change of momentum is change in P, is M, change in V, because velocity is what actually changes. And we change momentum by applying a force for a certain amount of time. So there's your formulas and your idea of change of momentum impulse. Okay, so there's the old saying that if you are in a car and you're going 50 meters per second and you hit another car that is going 50 meters per second, they say, or they have said in the past, the others, besides the physicists, have said, well, if you're in a car going 50 meters per second and you hit another car going 50 meters per second, it's just like hitting a wall at 100 meters per second. Isn't that what they say? Okay, so let's look at that a little more closely. Let's look at the change in kinetic energy first of all. And we're going to say that each car has a mass of 2m. Okay, so we're going to look at the change in kinetic energy of 1. Okay, so kinetic energy change is 1/2 mv squared. So the change in kinetic energy of one vehicle would be m times 50 squared. Do you agree? Or the change in kinetic energy of one vehicle would be 2,500 m. That's for one vehicle. Now, if we're smashing two vehicles into each other, you multiply that by 2. So we get a total change in kinetic energy, in this case, of 50 m. Okay? Or 5,000 m. Okay. Any questions about that? But if we would have a car, the same car, and we hit, so let's just say off to the side up here, that we hit a wall going 100 meters per second. Okay? The change in kinetic energy is still 1/2 mv squared. In this case, it's going to be m times 100 squared. So, the change in kinetic energy should be equal to 10,000 m. Okay, so we can say right now that there's something a little bit different going on here than just adding 50 twice to get 100, right? So in this case, we have a smaller change in kinetic energy. Change in energy is work, right? And work is force times distance, okay? Now, if we stay with the force times distance part, let's just look at that. Okay, so let's say force parallel displacement equals work equals change in energy, and in this case it equals change in kinetic energy, right? So what is the distance that this work is done over? Well, in a car, that is called, anyone know? The crumple zone, right? So if this is the original D, and then this is the new D, then the work that was done over that distance of crumpling. Any questions on that? Okay, so we could look at this, and let's just say it happens over 1 meter. So it equals force times 1 meter. Okay? So we have, for this case, we have 2,500, right, for one car, and it crumples over 1 meter. So the force then is 2,500 newtons. Do you agree with that? Now you can't force nothing, can you? So if this car is experiencing a force of 2,500 newtons, the other car has to experience that same force of 2,500 newtons. Okay, so we have a force of 2,500 newtons. So let's think about, though, these two cars being worked on at the same time. Okay, so we couldn't really do this so much with momentum because momentum is a vector, right? But if we think of these two cars being worked on at the same time, all of a sudden now our change in kinetic energy is, well, it's still force parallel displacement, but in this case it's 5,000 now joules, or 5,000 M would be the number, right? Because we used M in the last one. But how does that work then? Well, this is how that works. Okay, so if we're trying to figure out the force that causes this, we know Newton's third law says you can't push nothing, right? So we know that if this is the reality, the force that's actually causing this car to squish down, then there can be no more force, or no other force, no more, no less, due to Newton's third law. If he was right. Well, let's look. How does this change? Oh, I know how it changes. Now we're including twice the distance that this work is done over. Do you agree? So, if we go 2 meters, then we can see the force that is involved in this collision is still 2,500 M newtons. Do you agree with that? Okay, so let's look at this in another way, because we are talking momentum, and we are talking impulse, change in time times force. Okay, so funny thing is with this, it's a little hard to talk in classical momentum, I guess, the way we've been talking about it, because in reality, we know that there's a conservation momentum, right? What's the initial momentum of this situation? But before we do that, we're going to have to talk about the force thing, because we just have to rewind a little bit. We can't really rewind, though. So the other idea that we were talking about was hitting a brick wall. Force parallel displacement equals, in this case, we said 5,000 M for our change in energy. Or no, 10,000. 10,000, because we were going 100 miles, or yeah, 100 meters per second, 10,000. So the force for this then would be 10,000 times the mass, newtons. So we can see it's much, much worse. In fact, it's 4 times the force that you experience hitting 2 cars, or hitting a wall at 100 versus hitting 2 cars at 50. I might have something to say. And this D here is just 1 because it's 1 car going 100 meters per second. So there's still just a crumple zone of 1 meter. Now, if the crumple zone is a changing crumple zone, then that will change our numbers here too. So we can see that if the crumple zone is designed to crumple 1 meter every time, then that would happen. But in real life, this crumple zone would probably squish in 1.25 meters or 1.5. I'm sure it wouldn't squish in twice as far, because crumple zones aren't designed that way. So if the crumple zone was still 1 meter, then it would be 4 times the force that it would experience. Any questions on that? Okay, so now let's look at it from a momentum perspective, or a change of momentum. So impulse is force times time, and we'll say that, you know, the crumple zone is what determines the time of the impact. Because we saw that with the helmet, we saw that with the plastic bags and egg demonstration. So the crumple zone on a car extends the time of collision, which decreases the force that is needed to change this momentum. So if we look at this from a momentum perspective, we might get an understanding. But like I said, my first question to you was, there's conservation of momentum, so final momentum equals initial momentum. What is the initial momentum here, Keeley? So this is a little weird because the initial momentum on this is 0, right? Because momentum is a vector and we have a velocity of 50 in that direction, a velocity of 50 in that direction. As long as these are the same cars, the initial momentum is 0. And the final momentum is also 0. Okay, so if we were to say that the change in the summation and the change of momentum's absolute value, we would say that the total change of momentum, although this doesn't follow our whole conservation momentum vector thing, would be mv, but it would actually be 2mv, right? Because there's two masses, and their velocity, it wouldn't be even just v, it would be 2v. Do you agree? So it'd be like 2m times 100, because it's a relative velocity of 100 meters per second. Do you agree with that? So in this case, our change in, or the summation, or the absolute value change of momentum would be 200 m. That includes both masses. That includes the relative velocity of those two masses. Okay, and this is, and this right here is probably why people have this misconception. Because if you have a car that's going to hit a brick wall at 100, okay, that is going to be, that's 100 meters per second, right? So that'd be 100 m. It looks like I did this math wrong up here, because if I have one car with 50 m for momentum, and I have another car with 50 m for momentum, I get 100 m. So I did my math wrong a little bit, didn't figure it out until I did this, but this is where the misconception comes from, right? Because it looks like it's the same change of momentum. And if you don't think of momentum as a vector, it really is the same change of momentum. Because one car has 50 m, the other car has 50 m. When they're done, that change is, both those momentums are taken away, so the actual change of momentum, absolute value is 100 m. Just like it is here. So even with this misconception, can we find how the misconception is wrong? Well, I think we can. Because in reality, the relative velocity of these two cars here is 100. Do you agree with that? The relative velocity is 100. And then according to each other, they go all the way down to 0 for their relative velocity. So the change in velocity then is 100 minus 0, if we're talking relative. The change in velocity here for the single car is still 100 minus 0. So we're still seeing the same change in velocity. And how can we use this? Well, if you look at this as a crumpled zone here, and we'll just say that it maxes out at 1 meter, that change in velocity has to happen, this happens over 1 meter. Do you agree? Which means there's a certain amount of time that that's going to take, according to that velocity and that distance. But up here, we have a crumple zone of 2 meters, which we know this is going to crumple more than 1, but it's not going to be 2. So now we can see that, hey, this happens in 2 meters. That takes longer. to do, because we're slowing it's down from 100 meters per second relative velocity to 0 and 2 meters versus 100 meters to 0 and 1 meter, which means increase in time. And if you look at what we first started talking about here, if we increase time, we decrease force. So now we can see that it makes the physics makes sense both ways to show that, hey, crashing your car at 50 meters per second into another car at 50 meters per second is not the same as crashing your car into a brick wall that doesn't have a crumple zone at 100 meters per second. So let's see what the Mythbusters have to say about this, because I noticed they do have a little video on here. And this is the URL. If you're at home, you can check it out. We're going to check it out here.